Hi guys, I'm working on a demo board for the expressive ESP32-C6. The ESP32-C6 Room 1 module is a multi-protocol powerhouse designed specifically for the next generation of smart home and IoT systems. It supports the following wireless protocols: Wi-Fi 6, Bluetooth 5, Zigbee 3, Thread 1.3, Matter, ESP Now, and much more. In this video, we will go through the whole process from making and designing the schematic to routing and ordering the PCB. The main features for this board are an ESP32-C6 Wi-Fi module with 16 MB flash, an HDC3022 high-precision temperature and humidity sensor, a QWIIC connector, a USB-C connector for power and programming, buttons for boot and reset, user button, user RGB LED, a 2x5 pin SPI bus expansion header, a 2x3 pin programming header, and a power LED on the 3.3 volt rail. And for the mechanical side of things, we will have 4 3.2mm mounting holes, and the size should be approximately 50 by 50 millimeters, and I would like to have it on a 4-layer board design. Just before we start the project, I would like to thank PCBWay for making this video possible. Remember that there are a large section on PCBWay.com where you can find a lot of projects and inspiration from other makers. If you find a particular project interesting, then you can often directly order the PCB at PCBWay. You find my affiliate link in the video description of this video. Please use it and thereby support the channel. So remember to visit PCBWay.com. So here we are in KiCad 9, and let's head into the schematic design. And the first thing that we want to do is to set up some page settings. So for now we will use the A4 size, and we will have the landscape orientation, and let's fill in the date. And revision 1.0, and the title, that's an ESP, let's make the capital letters, ESP32-C6 demo board. Company, that's made by Morten. I think that's it for now. Press OK. And then you see down here, we already filled in some of the things in the title here. So we are going to design an ESP32-C6 into the design. So let's see if we can find that part first. Place symbols. And we have an ESP32 here already. And we are looking for the C6. That's the mini, and that's the room module. We'll go for this. This is a bit easier to solder than the mini one. And we'll place it over here for now. And normally I like to have the designator, here. Like that. And then the part number. Move, just press M for move, and like that. And let's put on some power on the 3.3 volt rail. Place power symbols, that's P, and we have a 3.3 volt one here already, like that. And we will have some wires, W, like that. And let's place some capacitors here. We would like a 10 micro or 22 micro and a 100 nano. So place symbols, and then we look for a capacitor, C small. This is this one. So let's place a couple of those here. And then Control D for duplicate. Like that. And let's place some ground. Like that. And I would like this to be a bit closer. M for move. Like that. W for wire. Like that. And this should be like a 10 micro for decoupling. And I would like 100 nano as well. And we can duplicate this. Control D. Like that. And we will call this 100 nano. So now we already attached 3.3 volts. This one a bit closer. Like that. And of course we have the ground pin here. So let's connect ground here. W, wire. And control duplicate. Like that. And then we have the enable signal for the ESP32. And with that we need a switch to reset it. It's actually a reset input. So let's make a few wires here. So we will need a pull-up resistor and a capacitor. So we can take this one, Control D, and place it around here, and that should be a 1 micro. That's what ESP32 they say that this could be a good value. And then we need a 10K pull-up resistor. And then we say R small. This one. And that will be like this. And that will be pulled up to 3.3 volts. Control D. Like that. And W. And that should be 10K. Like that. And we could move this in a bit closer. Like that. Alright, and then we need a button here. A switch, a reset switch that can pull this down to ground. Place symbols. And we will see if there's a switch that we can use a symbol, single. Yeah, I think this is a good symbol. We need... This one was with 4 pins. I need one with 2 pins only. This one. Like that. And then we need a ground symbol over here. Like that. And I would also like on all inputs where we have something where you can touch something, an ESD protection diode. So let's try and find one. ESD. This is this one, 3.3 volts. And we'll put it here. And just remove some of the part number for then it gets a bit easier to read everything. Like that. Where? And duplicate the ground symbol, and then I can move this up a bit. G. If you just press G, then it's easier to move. Then you move all the wires like that. So now we are happy about this part. And the next thing we would like to do is to place the programming header. Normally I like to program my ESP32s from an ESP proc module. That's an USB to serial UART. I normally put on a 6-pin header there. So let's try and find a symbol for that. And we need a connector. And we can just say collapse all here. And let's see, connector. Let's see, we need to remove that one because it takes all things with ESD. And connector, generic, and we want that to be 2 by 3. And let's see, odd even, this one. And I normally call them just pin 2 by 3. And yeah, we could keep that here. And wire. And we could just duplicate those. Like that. And we will have the signal up here also connected to the programmer. So we'll put a label on. And we will call that ESP enable. And we will use it down here. And we need the UART to be connected as well. L for label. And we'll call that ESP TXD. And this one will be ESP RXD. Like that. Can just take everything out a bit here, like that. And then we will have a boot pin, the boot mode. Just need to be, I would like them to be in the same length. Like that. And then on pin 2 we have 3.3 volt in this programming connector. Like that. And we will have a ground pin. Take it from here. something wrong here. The offsets. Gee, this looks fine. And then we can remove this bit. And G, we can move that. G, like that. And then here on pin 6 we have the boot pin. Place label, and we can just press L. And we will call that boot 9, because that's connected to pin 9 on the ESP32-C6. Like that. Then we have the programming header in place. Now we have all the necessary parts for the ESP32 to boot up. And yeah, let's have a look on some of the other signals that we would like to use here on the ESP32. I would like to have a user switch also connected to one of the I/O pins, so we can just take a part of the schematic over here and then just duplicate everything. Control D, and we just need to rename this signal here. We will call that user switch. Okay, and we will move that out here a bit, like that. I think that 10K and 1 micro, that's also fine. And we can move this up a bit here in the corner. We need to define some of the signals that we would like to have. We have some different IOs. There's the USB interface that's needed, so we can put some labels on here. And we will call that simply alpha label, USB, USB D minus, and USB D plus. Like that. And then of course we have the UART. And we'll put a label on that, and we will call that ESP TXT. And here we have ESP RXD. Like that. Then we have the two signals connected down here to the programming header. And then we need the boot 9 pin. And we need to connect that to pin number GPIO pin number 9. We will have a look on the datasheet in a second to see why this is pin number 9. And we can have a look here in the datasheet for the ESP32-C6. You can find this at Espressif, their homepage. And that's all the necessary information for designing a module with this. And you can see you can get it with 4 megabyte, 8 megabyte and 16 megabyte of flash. And this one has onboard antenna, and this one with the 1U inside there is a UFL connector on the board where you can connect an external antenna if you need that. But let's have a look on some of the chip boot modes. Here you can see that you need to have GPIO 8. You need to have that as a 1, and you can have a GPIO 9. That should be connected to a switch, so you can select which boot mode you want to activate. So we need to have GPIO 8. You need a pull-up resistor on that one if we want to put it in download mode. So let's put a pull-up resistor on GPIO 8. And we could take it from here. And we will put it around here. And then we are able to put it in the different download modes, the ESP32-C6. That's all what is needed. And we need to keep away, if you want to use some of the internal fuses and some other functions, then you also have to stay clear from GPIO 15. But you can read a bit more about that in the datasheet. And I will just keep this not used here in this design. So normally when I don't or decide to not use any signals on a chip, then I just put a small cross on the pin, this no connect flag. Then it tells me that I actually looked at this and decided not to connect anything to this pin. So you can see it here. That's a cross here. Okay. So we have here our user switch. We can duplicate that and put it up here, and we would like that to be connected down here in the bottom. So now we have all signals for the initial things. So we need an LED, a RGB LED connected, and we need an I2C port, and we need I would like to have an SPI port as well on a connector. So let's try and put those signals on here. So let's put some RGB LEDs on, some pins for that. We need like 3. And we need the I2C. One more here. Like that. And we will call this, we need a red LED in the RGB LED. And we will call this signal for R LED. And then we will have a green LED. And then we will have the blue. Just double click that one and then call that blue. And then we need an I2C port, SDA. And SCL. Like that. And then we would like to have an SPI port. I can just put some labels on here. So the signals that we need there is chip selects. And we need a clock. and we need MOSI, and we need MISO. Like that, and then a reset pin in that connector would be nice as well, and an IRQ pin could also be nice. So then in that connector we can have like a 10-pin connector where we have 6 signals, and then we have 2 pins for 3.3 volts and 2 pin for ground. But yeah, let's decide a bit later on where we should connect these pins. We have to look into the datasheet and see if that's possible, or we can just, you know, move them around as we please. So let's put that into the design a bit later. So the board itself should be powered by a USB port, a USB-C connector, and that should also be connected here to the USB D+ and D- signals. So we can just check and grab those, duplicate, and bring them over here. And I think we should try and find a USB-C connector. USB. And we have different ones here. I actually think this is the 16-pin version here. Let's take that one. Place it up here. Need to move those a bit away. Sorry. Move. Like that. And here we see the D+ and D- signals, but in between we would like to have some ESD protection, and there's a special circuit that I normally use for that. And that one is called USB C6, and that's a footprint. Let's try and place that one. And we could just place it out here. Like that. And then we need to tie together the 2 D- signals and the 2 D+ signals here. Like that. And we will label them D-, D-, and D+. And we need to put that on the ESD protection circuit as well. And we will have the label D-, and the D+. And then we need to attach the signals to the ESP. So we have the correct names now. And we need to put ground on like that. And we need to put some power on as well, 3.3 volts. And we can just grab it from over here. And I would like 100 nano capacitors for decoupling. Can put it around here, and then we can extend this a bit. G and W. G, move that up a bit. Like that. Then we have some ESD protection on our circuit. And we would like to connect the ground and shield over here. Like that. And the two SPU 1 and 2 pins, they are not being used. So we can place crosses on those ones, the no connect flags. Like that. So CC1 and CC2, we need to connect those to ground via a 5.1 kilo ohm resistor in order to be able to draw the 5 volt out of the USB connector. So let's place a small label here. And we will label that CC1. And this will be CC2. Like that. And then we can grab those, put down here. And let's find the resistor, duplicate this one, and rotate it. And we'll move this down a bit. So there we have the value. We will change that to 5.1 kilo ohm. And then we will rotate the designator here. Like that. And then we can duplicate this one. Move that and press G. Sorry, and then G here. And then we need to tie those two resistors to ground. Like that. Okay. Then we have the input voltage, the 5 volt coming from the USB connector. So I think we should move this down a bit here. And we can take this and move over here. Like that. And I would like to protect my circuit with a small fuse. Place, and so you can find a fuse. And I would like a polyfuse, small. And I would like it to be like a 1 amp polyfuse. That should be enough for this circuit. Like this. And then I would like a ferrite bed. Let's see if we can find one. small. And I normally use one called BLM 32 or 21, sorry, PG221. And that should be this one. Capital letters. Like that. And then we can move this down here, and then we can get this a bit closer. Like that. And then for protecting the circuitry, we would like a diode. So we will not get in touch with the 5 volt here on the USB connector, so we have this isolated off. So if we do something wrong on our demo board, then we will not disturb the USB power. And we will use a diode for that. Let's see if we can find a 1N5817, yes. But I need that one in SMD, but we can find that symbol later, or that footprint later. And then we need to tie this to ground. Can just move all this. Down a bit here. Something like that. And then, sorry, we need to connect that to our 5 volt rail, of course. Place power. And we have one called 5 volt here, like that. Awesome. So now we have a block here with USB, the USB circuitry. We have the ESP32 programming header, and we have a reset or a user switch here. So we need to go from 5 volts to 3.3 volts that our circuit uses. So let's put an LDO on. Just take the 5 volt here and the 3.3 volt. And let's find an LDO. Normally I use the LM1117, and that's also a very common LDO. So this is this one, and you can find that in different footprints. So this is actually the one that I normally use in the SOT223 housing. Let's put that on here. And we need, of course, 2 capacitors to stabilize it. And there I normally use a 22 micro. Let's grab some circuitry over here. Duplicate that. And that should be like a 22 micro. Something like that. And then on the output side, we need similar. See if they are in the same height. Looks like it. hit this circuitry. Then it has the same height, like that, W for wire, and then the center pin here is also connected to ground. Like so. And I think we would also like to have a LED showing that we have 3.3 volts. So let's check ground and 3.3 volts. And then we need a resistor in series with the LED. And that should be like a 1K resistor. And let's find a symbol for an LED. And rotate. Maybe there's another symbol called LED small. I can't remember. Let's try and look. There's one there. Delete and move. And let's connect those together as well. And let's call this green. Like that. And then of course we would like to have the RGB LED in place. And we can just grab some of this for that. Let's see, we also need the signals here from the ESP32. Let's grab those and put them over here. And then we need to find an LED, RGB LED. And I normally use one called CLV1L, this one. It has a common cathode, common anode. And let's just rotate it a bit like that. And in series with the 3 LEDs, we will have a resistor. Like that. And then we can connect the anode to 3.3 volts. And then when we pull down the signal on each LED, then there will be light in each one of them. And R7. And move. That's fine. And then we can grab the correct signals here, and this is the blue. And we would like that to be a bit closer. Press G, and we can move the wire. Like that. Then we have the green. Let's take this circuitry. Maybe I should have the 1K here, like that. Then they are not on top of each other. that. And then they have the same length. Then we can just grab the correct. We can just delete those first. Like that. And then we take the green LED. This is this one. And the red LED. Like that. And one other thing, we have the I2C port here, and they are going to be connected to a temperature and humidity sensor, but I would also like to take the signals out to a QWIIC connector. So let's try and get that in place. And of course, on the I2C lines, we need some pull-up resistors. I would like some 2.2 kilo ohm resistors. So let's grab the 1K here. And we need 2 of those. 2.2 kilo ohm. Like that. And then we need the QWIIC connector. That's a 4-pin connector, so we need a 4-pin connector. So let's remove this and find a connector. We can collapse all and then go to connector. One by 4. Do we need them in generic? This one. Like so. And you can Google the QWIIC connector. It's one designed by SparkFun, and there's a lot of informations, and they also supply a lot of different boards that uses this connector system, or you can make your own boards and then do the interconnection with the QWIIC connector. But I know that there is ground on pin number 1, and I would like to move that a bit around here so that we have pin number 1 in the bottom. And let's do that. And then pin 1 is down here. And we will find a ground symbol for pin 1. Like that. And then on pin number 2 we have 3.3 volts. And we can grab it from over here. Like that. And then on pin number 3 we have SDA. Like that. And then on pin number 4 we have SCL. And what we need to do now is to connect the pull-up resistors. Move this away a bit. We can drag those along here. And then move the signals out here. Like that. And here we have the pull-up resistors. Yeah, maybe I need a bit more space here. And then we grab SCL. SDA, and we need maybe a bit more room here, and we can put that in the same height as well. And then we could just add a small text box here. Place draw text box like that, and there we can fill in the color on the cables for the QWIIC connector. So we have the ground. There we use a black wire, and then we have VCC. And here we use, of course, a red. And we could just have that only the first one in capital. Then we have the SDA. And that's the blue wire. And then we have SCL. And that's yellow wire. Like that. And we need it a bit larger. Just pull down here. Like that. So we have a small info box here. So let's try and design in the humidity and temperature sensor, and I decided to use the HDC 2033 from Texas Instruments. I used that one before in some previous designs. So let's see if we have the symbol in here already. And we have it here, 3022. Oh, sorry, it's called 2033. I think there's some misunderstanding here in the labeling, but that's fine. Let's clear that up right away. So I have the datasheet here, so it's actually called HDC 3022. 3022, yeah. And let's give it the correct name. So we can just change it here. 3022. Like that. And here we see we have the SDA and SCL pins. So let's find those. And put a wire on here. And the labels. Like that. And then we need to check up on the address pins and the alert input, what to do about those. So let's have a look in the datasheet. What about address and address 1? So let's have a look down here. If there are some informations about the pins. So we can see here that if we put ground on address and address 1, then we have address 44 hex on the I2C bus. So let's go ahead and tie those pins to ground. Something like this. And then we need address 1 as well. We'll also tie that one to ground. And then of course the power is 3.3 volts. And let's grab 3.3 volts. And we also need to bypass it by a 100 nano capacitor. Take it from here. And let's connect that to 3.3 volts. And grab the power symbol here. Control D for duplicates, like that. And then here we have the ground pin, of course. We need to put that to ground. And then we have the alert pin and reset pin. Let's check up on those pins. Let's see here in the top. Normally there's a description of the pins here in the top, but maybe this is not the case with this schematic or this datasheet. We see here the alert pin is an interrupt pin. If not used, must be left floating. So we can just float that pin, and we just put this no connect flag on. No connect flag here. And then we have the reset pin. Reset. Active low internal pull-up resistor to VDD, if not used, tie to VDD. So we need to connect that to plus 3.3 volt if that's not used, and we will not use it. And then there's also some information about the sender pad here. The thermal pad can be soldered or left unsoldered. If choosing to solder the thermal pad, attached to a pad that is connected to ground. So we can just leave that unconnected, no problem. And we need to connect the reset pin to VDD. And we can easily do that here, wire, like that. So now we have our temperature and humidity sensor connected. And let's focus on the SPI port, or the auxiliary connector, the 10-pin connector, where we will have our SPI pins, or we could also just use them as general purpose I/O pins. So let's find a 10-pin connector. And we should use a generic connector, generic. And we need one 2x5, odd even. This one. And I also call this one just pin 2x3. Sorry, 2x5. Like that. And then I would like to have pin 1 and 2 connected to 3.3 volts. Something like that. Control D. And then we have the same length on the pin side, like that. We can just duplicate that. And then we have our 3.3 volts. And then we can put our ground on pin 9 and pin 10. like that. And then we have our signals defined over here. Duplicate those, and then we need to arrange them. And we will have the reset pin here, or let's start with the SPI port, MISO, MOSI, and there we have the reset here in the top. And let's have the chip select over here. And we will have the clock symbol or label and the interrupt, like that. And of course you can configure this to be either, you know, GPIO or SPI or some of the other peripheral settings that you can have for those explicit pins. So this is just like a connector where you can connect different things to. And then the last thing I would like to get in place is the boot switch. We need that one, of course. I was about to forget that one. So you can manually put the ESP32 in boot mode. So let's take that one as well. We can just grab a piece here and move this down a bit. Like that. And this should just go directly into pin number 9, boot 9. So we can just grab that symbol, or the label, sorry, and move it up here, make it a bit smaller. Like so. And we also need an ESD protective diode on that pin. Like that. Sweet. So let's have a look here. The main remaining things we need to make sure of is our SPI port. And let's have a look in the datasheet for the ESP32 room module, where we can place those, or if we can use them on whatever pins we want. So let's try and find some information about the GPIO pins, if there are some specific ones. Let's see, what do we have left? So that should be on GPIO 18 to 21. Could be an idea. There should be nothing special about that. You can use that as a general purpose I/O or some SDIO signals. And let's have a look if there are something special about the SPI. Can just try and see if there's something specific. SPI controller. Some specific chip selects. So there are 3 SPI interfaces, SPI0, SPI1, SPI2. So we would like to use the SPI2 because 0 and 1 are reserved for the system, and SPI2 is available for the users. So let's see if there's something specific in here. For the SPI2, let's see if there's something special up here. SPI2. And let's see what are the red ones. That might be something that you are not allowed to use SPI on. QFN32, QFN40. So let's see what the right here can be mapped to any GPU through signals of UART0 and SPI2 interfaces can be mapped to any GPIO pins through the GPIO matrix, regardless of whether they are directly routed to fixed pins via the IO mux. So we can just move them as we please, it says here. So let's connect the SPI port to some of the GPIO pins here, and then we are ready. So let's just say that we want the chip select here on pin GPIO 18. Yeah, then we have this on a nice line. And then we have the remaining signals here. And then we need to move the clock signal here. MOSI. Put that there, and MISO there. Then I would like to have the reset and ERQ signals here. Like that. And then just place the reset up here and the ERQ signals here. Like that. So now we actually got all things connected and wired up. I think it could be nice to get everything divided into small blocks and make a small label about what each block do. So let's try and draw some lines in order to divide everything. And the first thing we have up here is, of course, the USB signals, or this USB port. Maybe we can move this a bit further over. Let's try get this down there. And then we can move this a bit more over there. And we can also take this and move a bit. Press G. Like that. Then let's place some wires. Draw lines. And we can try and make the first ones here. So it's a bit off, this one. Place line, draw line. Like that. And then we can try and divide this. Maybe we need a bit more room. Like that. I think that looks reasonable. And then we can take and divide this one as well. Maybe we can move this a bit further to the left. Yeah. And we will move this down a bit here in the corner. And the LED here in the middle. And let's try and move the LDO here. Like that. Then maybe we can get this one back a bit as well. There. Then it's not that cramped. And we can try and move this in a bit. We can have a line here. Line. Like that, and then we can divide. Like so. And let's see if we can get this in. Maybe this is just a bit too high. Let's move this down here. You can always move these power labels down here. Like that. And then we can take the ground ones. Like that. I think we are close by. Let's place some wire or some lines. Place lines. Like that. And let's try and see what's possible here. Maybe we can move this up a bit. Like that. Let's see how this looks over here. Place line. Place line. Like that. Maybe we need to tweak this a bit. Like that. Yeah, I think that's fine. And we can just leave this. And put, yeah, let's put some descriptions here in each corner about what each block does. So let's place some text. And that's called USB-C. And maybe we should make the text size, I don't know, 200 maybe. Maybe that's a bit too much. Let's make it 150 and see how that looks. Let's try that for now. And this is the LDO. Maybe this is a bit too big still. Let's make it 100. LDO. And 100 here as well. And what do we have here? We have RGB LEDs. Like that. And here we have the QWIIC connector. That. Then we have the boot switch. Like that. And let's move it over here a bit. Like that. And we could move everything down a bit here. Like that. And let's call this I/O, this one. And what do we have here? I have a temperature and humidity sensor. Temperature plus humidity sensor. Move like that. And then we of course have the ESP36 or ESP32-C6 module. ESP32-C6 module. Like that. So now we have a nice overview of our design. And I think, yeah, maybe we should add here in the schematic some mounting holes so that they will be included automatically when we open the PCB layout. So let's place some symbols for mounting holes. Mounting hole. And you can connect them to ground if you want, or I think I will just leave them without any connection. So we can put them here. And we need like 4 of them. Like that. Save. I think that it's fine that they are placed here. So when we have all the parts in the schematic, then you know the designators, they are just moved around, and we deleted some symbols and so on. So they are just in a huge mess right now. So we can just make an annotation of the designators. So we just say tools. And we say annotate schematic. And then you can design the order of how the designators, they will be updated, and they will be done in this horizontal way. You can choose a vertical way if you want that. And the entire schematic, and we will reset all existing ones, and we'll start from 1. And then just press annotate, and then all the job is just done automatically for us. So that's quite a strong feature. Let's remember to save the design like that. And one other thing we can do is we can prepare the schematic for the PCB. And normally I do it here in edit symbol fields. There we have all the different variables for this design, and we can see which footprints has been assigned to all the parts. And there's also links to some of the data sheets. And before we start the PCB design, then we need to decide the different footprints for the parts that we have filled in here. And if we don't have a specific footprint, then either we can design our own, or we can try and find it online somewhere. But let's try and assign some footprints and see how that goes. Also in here you can add your own fields, so you can just, if you for example also want to assign, you know, part numbers from Mauser or GTKey or something, you just press plus here and you say Mauser like that, and then we have one called Mauser. We can hide them if we want, some of the columns. Let's exclude, let's try and hide those if that's possible. This is this one, and this one, and do not populate this one as well. And then over here you see the Mauser one, and then you can start filling in the part number for the mouse or parts, or if you want a GT key one as well, then just add it here. And you can also hide that and show it again. But let's concentrate a bit on the different footprints, and you can see that we have here 3 100 nano, and that should be like a 04, 02 footprint I would like to use for those ones. So let's try and see if we can find that. So capacitor SMD, and we have an 0402 metric, like that. And for the 1 micro, then we would use a 0603. That one. And for the 22 micro, then that we would use a bit larger ones, 0805, I think. Would be fine. Then we have the diode. There was this leaded one, and I would like to use one in SOD 123. So let's try with that one. Is there's one called SOD 123? Yes. We'll use that one. For the green LED, we'll just use a footprint and 0603. Let's try and find an 0603 LED. There's one there. And for the RGB LED, we will use a PLCC 4. Yeah, this is fine. The polyfuse, I think that we should use like a 1206 footprint for that one. Let's try and see if there are some polyfuses, or maybe we should just call that fuse. .1206, and this is a an 0805 ferrite bed. Let's find an inductor, L0805 maybe. There's one here used before. And the mounting holes, that should be some 3.2 millimeter mounting holes. Mounting holes, 3.2 millimeter. And there's some different designs here. Let's just take the standard one. And then we have the USB connector. Let's see. That's this one that I normally use. And then some standard pin headers. 2x3. And I have a 2x5 as well. That one. And then here we have the QWIIC connector. And that's a JST connector. Let's see if we can find that one. I think it's actually this one here. SM04B SRSS. Yes, this is the one. Then we have a lot of resistors, and I will just take some 04, 02 ones, and then we can just copy this one and copy that to the next. And then for the switch, yeah, let's see what we can find there. Did I use some of those before? Yeah, there's this angled one. Let's have a look on which one is this with the 2. We need 3 switches. Yeah, and I want one of them to be an angled one, coming from the side. So we just need to look at which one that should be, and that should be the user one. So let's say apply and save this and say OK. And then we have the user switch here, that's switch number 3. So I want that one to be different from the other 2 ones. So let's go to Tools, Edit Symbol Fields, and then go to the switches, and then switch number 3 should be this angled one. So this is this one. Sorry, something happened to KiCad, it just did fall out. Let's try and boot it again. I don't know what happened. Yes, okay. And let's try and go into Tools, Edit Symbol Fields one more time. And we have the switches, and it just needs to load all the footprints one more time. And let's try and find the switch again. Maybe it's in my libraries here. Yeah, that worked. And let's apply that. And then we need the 2 small buttons. And we'll use this one. And then let's check here on the remaining ones. That's in ESP32-C6 and the ESP32-C6 module footprint, the LDO footprint, SOT223, and that's an TI footprint. So now we have assigned all footprints except the first one here. So that's a 10 micro, and I would like to use an 0603 footprint for that one. So we can just copy that one, place it like that. Perfect. And let's say apply, save schematic, and continue like that. So now the schematic is done. We have defined all parts, connected everything, and we have named all the footprints. So we are ready to start the PCB layout. But let's just take a small break and then see you later for the PCB design. So welcome back after the coffee break. Let me just show you one thing here before we head over to the PCB layout. If you want to create a PDF of the schematic design, then you could just go up here, File, and then to Plot. And then you can see you can have different output formats here. The output directory is just the path where your design is. And everything is pretty much just standard. You can select if you want a color output or a black and white. Let's take color. And then you just say plot current page. And let's have a look here in our design. So you see here we have a PDF here with our design. That's quite nice. Quite handy. But let's head over to our schematic here. And from up here we can say Tools and update PCB from schematic. That will take all the parts from the schematic and then fill in the footprints into the PCB. So let's try and see if that works for us. So we see here it added a lot of footprints, and there are no warnings, there's no errors. So let's try and update PCB. And we have some warnings. There are some parts that has no pin connected to it. That's the mounting holes, and we have some extra pins on the QWIIC connector, and yeah, that's basically it. So no problems. Yeah, and we see here pad number 9, that's the humidity and temperature sensor. We don't connect that to any signals or any power or any grounds. So that's fine. We're happy with this. And there we have all the parts in a huge pile. So my goal was to design a PCB that are 50 by 50 millimeters. So I think that should be possible. So let's start checking that our grids are as we want. I would like to start with a 1 millimeter grid. Then it's easier for me to place a PCB here that are 50 by 50 millimeters. And let's head over here to the edge cut layer and place a rectangle. Then this is the outer size of the PCB. So we get that here. And we can just briefly see, okay, can we place all the parts inside? So if everything was crammed together, that would be this area. So definitely we can have everything in a 50 by 50 millimeter PCB. So that's it, like that. That's the size of our board. And we can round some of the corners. So, and we would like that to be with like a 4 millimeter radius. And then just like that, then we have rounded corners. And we can see if that fits with our mounting holes. Let's try and move those in here. That looks awesome. So let's take those and fill in here. Like that. Then we have our board here, and then we just need to place the remaining parts. And I would like this corner down here to be 0.0. You see the numbers here. We can just reset those to 0.0 by doing this. Just press space, but we can also move the other coordinates down to that corner. So we just say place grid origin, and that should be here. Then you see they changed to 0.0, and we have dx and dy to 0.0 as well. and we are still on a 1mm grid. We can see that up here, and we can of course change that to whatever we want. But for now, I will keep it on a 1mm grid. So the most important thing is to place the ESP32 module. So we can just grab that. So you just go over here with the mouse and then just press M for move, and then we can see all the RAS-nets, they follow here. But let's see, we need to have the antenna outside, and we have the middle there, so we can put some measurements on, so it's easy for us to see where we are and where the middle are. So let's take that on user 2 layer, and then let's place some dimensions. Place draw dimensions, and let's just have one here, so we can see, and 1, 2, 3, 4, 5 millimeters out, and we would like to check this one as well. And that's also 50 millimeters. Like that. And let's find the middle here. Can also do that. That was 25 millimeters. This here. Then we know we have a center there, and we would like to have this module here in the center. It's approximately here. And let's have the antenna outside here. We are on this 1mm grid. We can just lower that to 1/10 of a millimeter. There, exactly. And what would look nice if we have the USB connector in the middle as well. So we can just go up here, find the middle. Yeah, this is the middle. Then move down here. And I want that, if you put that into an enclosure, then I would like to have the USB port a bit outside the PCB. So let's make that here. And we see down in the bottom that X is 25 millimeters. So we are in the middle. Sorry, like that. And we can just remove the silk screen for the mounting holes that are not needed. Like that. And we can take that and put over here. Like that. And I would like maybe the reset button or the user button to be here on the side. Maybe over here somewhere. Like that. And the QWIIC connector, can have that up here. Close to the edge, and with the LDO could be around here somewhere. Programming header, that could be up here. Can move this down a bit here. Then there's some free space for the programming header. Like that. Then we have the SPI port. Something like that. I think that's fine. And then we have the RGB LED. Should we replace that one? Can you see where we have the signals coming from? They are from up here. So I think that's fine. Then we have the temperature and humidity sensor. Can move that up here somewhere. I think that's a fine location for that. Then we have the two buttons for the programming and reset. Somewhere around here. Like that. Then there's room for some text around the switches. You see the X and Y 45.2. Then they are aligned. And need some text around the SPI port here. Maybe we should rotate it a bit so we have pin 1 up here in the top left corner. We can always move that a bit around when we add some text and labels to the different footprints. Maybe it would look nicer to move it a bit around, but now we have the most important things placed. Can just take the ESD protection here for the USB interface. Maybe this one will get in the way for the USB signals. Can put it down here. Then we have a clear path for the USB signals here. Yeah, then we have the diode and the fuse and the ferrite bed. Then we have the power LED. and then a lot of resistors. But let's focus on the power supply for a second. The polyfuse was the first part. Let's place it around here. 5 volt coming in. And then to a ferrite bed bead. Something like that, and then to the diode. Something like that. And let's find the 2 decoupling capacitors. That was those 2 guys. For the LDO. So the capacitors should be close to the pins here. The LDO. Like that. And then we can have the LED for indicating power is on. Can have that out here. Then there was a 1K resistor. I think this is maybe this one. And we can move that down here in series with the LED. Then we have the ESD diodes for the switches or buttons. Move that over here where they need it. Then we have a 100 nano. One was for the 3.3 volts near the ESD protection. Then we have one up here for the power supply for the ESP32. Something similar to that. And there we also had a 10 micro. So this was C1. There we have that one. And the 1 micro was around the buttons over here. Let's move those over here. And then we have one more 100 nano. I think that was decoupling for the temperature and humidity sensor down here. Like that. And we have 2 4K7 that was for the pull-up for the I2C pins. Or that was 2.2 kilo ohm. Take them over here. 5.1K. That was for the USB port. Somewhere here. Then we have some 10K and some 1K resistors. And what we can do is go back to the schematic, and there we can actually highlight the ones that we are in question. So we have this one near the ESP enable signals, and we just mark it here, and if we go back to the PCB layout, then we can see this is this one that has been highlighted here. So we need to find the ESP enable. So this is close to this. That's a way to do it. And we can just try one more time. There's one more resistor we need to find. That's this one for the user switch. And that's for the right angle switch here. And we also need a capacitor for that pin as well. So this was C7 and D5, so we can highlight both of them. Go back to the layout, and there we see those two remaining parts. They need to be up here, around here. Like that. And then we have this one micro, needs to be over here. ESD, D3 here. And D2 over here somewhere. And maybe one good idea would be to rotate these two buttons, because we have ground on the inner side, and it's easier to route the signals if they are reversed. But we can do that a bit later. Let's find the last parts up here. We have some 1K ohm resistors and a 10K ohm resistor. So let's see where those would fit in. We have the one for GPIO 8, that's R2. And we can move that close to where it's supposed to be used, around here. And then we have some 1K resistors, and that's the resistors for the LED. So now we have all the parts inside our board, and we can just take and rotate switch 1 and switch 2 here. Like that, and then we can take the parts on the inside. Like that. Save. We would like to save this. And we could have a look on it in the 3D viewer. So this is how our design looks like. We can see there's one missing 3D model here for the LED, and I would like another model here for the ESP32-C6. I think I have another model for that one. Let's check that out. We can just close the 3D viewer again. And let's have a look here on the LED. And then we can say 3D models. And we can see if we can find one. So this is actually this one. And it actually fits quite well. Okay, to that one. And then we have the ESP32-C6 module. see if I have another model for that one. And we can hide the old one, and I like this one a bit better. And we can just offset it. See if that was enough. A bit more. Yeah, I think that's actually perfect. Save and view 3D viewer. I think everything is in place now, looking great. And we can start routing and start getting some text on the board. So let's get started. So the most important thing is to route the USB signals, because we cannot just move them around as we please. So I think that would be beneficial if we did the routing of those first. And this will be a 4-layer board, and there's a stack up for this this PCB, and I normally use PCB way for this. And there are a description on how to make your stack up using PCB way. That's the important things about, the build-up of the layers. This will be a 4-layer board, and we need to know the distance between layer 1 and layer 2 in order to make a 90 ohm signal there, traveling from the USB connector to the ESP32-C6. So let's have a look on that. We just need to head into PCB way. And let's have a look if we can find the description. We need to go to product capabilities, and we need to find something about the layers. Maybe we can just search for it. Layer stack up, there it is. So there's a lot of dimensions here we should look at, but here we have a description of 4-layer boards. So let's see, 4 layers, yes. And we would like the board to be 1.6 millimeters thick. And we can just search, and that is like a total of 21 different ones. But I think we should just take the first one here. So we see that there are a distance between layer 1 and layer 2 of 0.196 millimeters. So that's one of the important parameters that we need to insert into our calculator that can calculate the width of the traces that we use when we design our 90 ohm tracks on the board for the USB signals. So one parameter we have here, the distance between layer 1 and layer 2. We can just have a look here in layout, and we say file and board setup, and we need to insert here, of course, we want a 4-layer board, and we could insert the dimensions here, it's not needed, but we need to look at the design rules here. And one of them that are important is the net classes. We want to make a specific net class for our 90 ohm impedance tracks, and we should select which traces that are going to use that net class. So we have our standard or default net class here that says, okay, we want a clearance of 0.2 millimeters, track width of 0.2 millimeters, and the via sizes and all that. But we want to have a specific net class for the USB signals. So we will add a net class and we will call that 90 ohm and USB div. And we will just set the clearance to 0.1 here in the beginning. Then we will need to set the width and gap, and we need to calculate that, and we will do that with a special tool. And let's see if we can find that tool. That was, maybe I have it here in my Saturn PCB toolkit. Let's see if we can use that one. Apparently it's going to install something on my computer now. Yeah, let's just do that. And let's start it. So here, this is quite a nice tool. You can do a lot of different calculations in here. What we would like to do is to look at our PCB. This is some via properties. So let's see what we can do here. Differential pairs. So this is actually the one that we could use. And we are in millimeters here. We would like to do it in metric. And we would like to do that for USB 2.x. And we want 90 ohm. And they say, okay, plus minus 10%. That's in between here. And there is already a calculation here that gives us 100 ohm, but we want it to be closer to 90 ohm. But we also need to insert the correct data here. We had the height from PCBWay. That was 1.196 millimeters. And what 35 microns in PCB copper weight, standard FR4. That looks okay. Then we can try and tweak these numbers. We can just try with a smaller number here, 0.15, and the spacing 0.15 millimeters. That gives us 99 ohm. Let's try and see what happens if we go further away. That goes in the wrong direction. What does this do? So we actually have very close to 90 ohm. Then we are in the wrong direction. So if we have a conductor width of 20 or 0.2 millimeters, then the spacing So if we make the spacing between the signals 0.16 millimeters and the conductor width 20 or 0.2 millimeters, then we have a differential impedance of 90 ohms, very close to that. So we can plot those numbers into KiCad, and let's go in here. So we have the width of 0.2 millimeters and the gap of 0.16 millimeters. And then we can select or assign that net class to specific nets. And we could just take that was something USB. Do we have some USB ones? Or we could just maybe say add here. Let's see how we could do that. Something with USB. We need to find those nets. Let's see how we do that. And we say just OK to this. Then we find the nets here. So that's D plus and D minus, and USB D minus and USB D plus. Port setup, net classes, D plus. So then we have D plus, and we should assign that to 90 ohm net class. Add one more, slash D minus, and that should also be 90 ohm. Sorry. Just say save file, port setup, and add two more. That should be slash USB D minus. Okay. I don't know why that breaks out. Slash USB D plus. Like that. So now we have assigned those net classes or that net class to our USB signals, and then we should be able to route the differential pairs. So let's see if this is possible. Route differential pair, and then it automatically selects the one with D plus and D minus because it knows that they match together. And we would like to say, okay, what do we have D minus over there? Where do we have D minus down here? So we can go in here like that. And then we should route plus around here to plus, and we should go from minus to minus. So we can do that here on the back side. That cannot be done with differential routing. So we should just take this one and route that like that. like so. And the D plus, we have to route that over here, like that. And then we have one more differential pair to route. And we should try to do that. Route differential pair. Like this. I don't know why it does not want. Maybe I should remove some of these parts. And then say route differential pair. Check if there's something wrong here. D plus and D minus, that's fine. So I can just try and do that from scratch. Like so. So they connect together nicely. So let's say route differential pair. Oh, there's something wrong when it... there's a rule we need to look at because it became green. So maybe there's something here with the clearance. So we just say 0.115 here. Maybe that rules will override what we're trying to do. So let's try and reroute this again. Like that. And let's say route differential pairs. And now we don't see the green wires. And there we go. That was a mistake from me. I needed to have the spacing a bit smaller. So there we have it. Now we have the USB signals in place. Let's try and get some power out to this one. And maybe that can be done here. Like this. And we'll put a wire in here. And then we have the ground. We can take that out here, so there's no problems. Like that. So we need to assign a ground layer to layer number 2, and layer number 3 will be for 3.3 volts, and the bottom one will also be a ground layer. So, or signal and ground layer. So let's assign a fill zone or a rule area. So we will do that on a 1 millimeter grid here. Sorry, we need to place a fill zone, and we need to get out of user 2. We need to be in one of the other layers here. And we can see, okay, we want layer 2, 1 and bottom layer, and we need to have 3.3 volts on that, or ground on that. And we want the clearance to be 0.15 millimeters. Minimum width 0.2 and 0.2. And the spoke width could also be 2 millimeters, 0.2 millimeters. And then we just go around here. Like that. Then we have defined that we have ground. And I would like to define one more for the 3.3 volts for layer number 3. And that's that one. And we would like to have 3.3 volt on that one. And that's 0.15 as well. Like that. Just go to each corner. Like so. So now we see here that the via here is now connected down to layer number 3. And this is layer number 3, the brown one. So that's the via is connected to that power plane. So now we can route some of the existing wires. There's a lot of work to do ahead of us. So let's get into it. I need to move this a bit further away because I want to have some labels around this one. Maybe it would be beneficial to rotate it a bit, maybe. Let's see. Would that make sense? No. Can have these ones a bit further out. Like that. It's just because I need some text around the connector here. What I could do was to take this capacitor and put that on the other side. And go down in. And then let's see. Something similar to this. And there's just a small thing there. Away with that one. Just let's make sure that we can route the ground out from there. And we can get a bit closer with that one. Think this is a bit better. Then there's a bit more room for the text here for the connector. And we could try to move this a bit closer. Now we can turn off the fabrication layer. There was a lot of info that we don't need anymore. So let's see here. User switch. That's a pull-up resistor. And capacitor to ground. And some ESD protection. We could have that there. Let's try to move this around a bit. Something like that. Like that. Let's see how that pans out. Like that. Here we have the programming connector. Let's try and route the signals for that one. We have 3.3 volts is already there. And then we have RxD and TXD. They're coming from up here. And we don't want to have something looking like that. And then we have the TXD line. Just take that out here and put a via. And then go to the ground layer or to the bottom layer. Like that. Let's move that a bit to the middle. Should decide for another grid. Can just take that. Like so. And do we have something important up here? This is just ground. ESP enable is coming from up here. You could just put a VR here. Go to the bottom layer. Oh, there's an issue. like that. There we have the user switch to go to the top layer. That. Fill in some mirrors. The user switch is up here. That's. Then we have the enable. And we want to go to the bottom layer. Like that. And there's ground there, fine. Then we have boot 9. And it's up there. We can just go to the bottom layer as well. And there seems to be, is that called boot 9? There must something missing there. Something went wrong, we can just delete that. Try again. That's, and then we have boot 9 here. Yeah, that's a bit difficult. Let's see how we can solve this. Yeah. And then go to the top layer or bottom layer again. Like that. And 3.3 volts, that's fine. And ground, that's fine. Ground, that's fine. And we have an LED signal going down. Let's try and route the 3.3 volts up here. Like that. Put here there. Yeah, there. and we are there. Then let's see here. We have GPIO8, and we can connect that to via to 3.3 volts there. Then we have the SDA and SCL lines here. Let's see how we can arrange the pull-up resistors. Let's pull up resistor for SDA. And that's for SCL. Like that. Then we have an LED over here. The RGB LED. We could move that in here. Like that. Let's try and route that signal, and then one more resistor. That. And the third. And we want that connected to a 3.3 volt net. Through a wire there. There's a via here. Like so. And connect 3.3 volts to the regulator, 5 volts. And we have 5 volt coming down here from the diode. Like that. Then we want to find a way to connect the 5 volt coming out from the USB-C connector here. Could move those on the other side. Like that. Place a via there. Go to the bottom side. Place a via there. Like that. Then we can just make the lines a bit thicker. See, could that be 0.5 millimeter? 0.6 millimeter? Yes. Then we can just press this one, press U. And then we can just properties 0.6 millimeters. And we want to move this via there. That. And then we can just highlight this one, press U, then it selects the whole net. And then we can just make these a bit thicker as well. And then this one, like that. So now we have the power in place, and we could just try and figure out how to connect the two 5K1 resistors here. Drag that down a bit. And move R3 down here. And have R4 close by. Like that. And we can have the designator over here. Like that, and those are going to ground. Something similar to that. Then we need some I2C signals down here for the temperature and humidity sensor. So we have the SGA line here and the SCL line. I think we need to go to the bottom layer. See if we can find the I2C signals over here. That was one. Might have to go over here. that. What else do we have to connect here? We have a ground. Connect that to a VR. 3.3 volts on 2 pins. And then a VR here. Ground, just a VR. Like that. Yeah, for that one. And some vias here. Like that. There. Like that. And we can connect this capacitor to ground as well. Yeah, there. This is automatically connected to ground. Yes. Place a V in there for that one. So now we have the LED. And yeah, we would like to have our 3.3 volts being connected here. I have 2 vias here. Then we have a connection from the top layer to the plane, the 3.3 volt plane here. Then we have the bypass capacitors grounded. Then let's try to find the LED. It's just a small dent there. X. Yeah, then go to bottom layer. Then we need to catch the LED signal up there. Just go through a via there. And then route here from the top. Like that. And then we have 2 more LED. Let's see. Yeah, and we need to cross the USB signals on the bottom layer. that out of the way a bit. That. Let's place a via here. And we need to go to the bottom layer. Sorry. That's like that. So now we have the signals for the LED, the RGB LED. And this is one is connected to 3.3 volt layer. Save everything. So I think what is missing now is signals for the SPI or GPIO interface. So we have reset and interrupt here. And we can just move the vias up here. Then they don't have to cross. Oh. So behaving a bit strange, this one. Like that. Let's place a via here. Get rid of that one. Like that. And then we can route reset out here. And interrupt. And we don't want to get too close to the USB signals. That. Then we have the remaining SPI signals. We can maybe route them here on the bottom layer. See what we can do here. There's a via there. here, there. Like that. And there's one more. And we can get rid of those two small tracks down. And this should be moved a bit. Like that. Then we need SGA and SCL. They need to come from up here. So we can just continue this one on the bottom layer. The SGA line. SCL line. Could also move to the bottom layer. There. So I actually think we have most of the tracks routed now. So let's try and make a copper pour. So we see the top layer, sorry, the bottom layer. We can try and turn off the other ones here. Like that. And here we see the ground pins are connected to the plane. And we can try and have a look on the 3.3 volt layer here. See, the ground is not connected, but the 3.3 volt via here is connected to the layer. So this looks perfect as well. And let's have a look here on the top layer. We need to have the correct distance here on the USB signals. We need to have like 3 times the thickness of the track here, so that's 0.6 millimeters that we need to have in clearance on the USB signals. So we need to take care of that. But else, I think it looks quite okay. So let's have a look on the clearance of the USB signals. And here we see the clearance is much better now. There's some issue with one side. Let's try one more time. USB D+. It's really strange that that has not, maybe that's not a part of the net class. So we just need to do that. And then try again. And then there we have the correct width or the clearance for the USB. Of course, there will be a problem here because we are too close to the pad, but we cannot really remove the pad anywhere. Track. Yeah, we cannot really do that any longer because we will get too close to the USB signal, so that's fine for now. And of course there will be some things here when we do the design rule check. But yeah, that's the way it is. I think I'm happy with the routing so far. So let's have a look in the 3D viewer if we are satisfied with how everything looks. Like that. And what should we do now? We could have a look on some of the silk screen, and we need to put some text here on the connector so it's easier to connect the pins here if we want to add something. So, or add some wires, so let's have a look on that. So let's add some texts here, and the size that we use is 0.15 for the thickness and 1 millimeter for the width and height. And that should be on the silk screen, top silk screen layer, 1 and 1 and 1.15 millimeters. Right, and that should be plus 3.3 volts. That should be around here. And now we just duplicate then we can just double click them and rename them afterwards. Let's reset. Mosi. Miso. And ground. So down here you can just remove all items when we select and then go for text. Then double click here. That's much easier. Then we don't select the wrong things. Interrupt. Ground. And let's try to align some of the texts. And we'll get a bit close here to that one. Maybe we can just move it in here. Approximately, we will do it perfectly with a tool in a second. That. So that's the strings for the GPIO header. So we can align this. And let's align distribute, and we want to align to the right. And we want to align so that we have the same distance in between the centers. And then we can just move them a bit closer, like that. Then we can do the same for the 5 other signals or labels over here. Line, then to the left, and then align, and then the same distance to centers. And we will move them over here. Let's have a look. So now we just have to move the remaining designators. Let's try and do that. Make it look a bit more pretty. D5 there, R6 here. Don't want to place that on top of a VIA, then some of the text will just disappear in the production. G2 there, U2. It's fine. C3. That's J4, that's fine. Can move those ticks up on top here. That's D1. Fairbeat fuse. Like that. Take U form, put over there. C2 there. D3, that's fine. Let's take that away a bit. We can put that on top here. And we could just add some texts. place text. We would like to call this reset. So we can see this is a reset button. And we want to call this boot. Like that. Switch 3, we can move that up a bit here. Like that. I think that's fine. Let's have a look in the 3D viewer. Did we miss any texts or anything that are misaligned? I think that's cool. Can just add a bit more text. Place text. HDC32. And that should be, of course, on the silk screen. 1, 1, and 1, 5 here. Where can we have this text? And I would like to have my YouTube logo, or the YouTube logo as well. Place footprint. I think I have that as a footprint. If there's room for it. That. Save. And let's have a look on the back side. We could put a KiCad logo on there. And KiCad logo. I think that's fine, but we need to put that on the other side. So we just have it here and then press, well, just mark it. Or we need to say all items. And then you just press F for flip, and then we have it on the bottom side. We can put it here in the middle. Place texts. Powered by. We need to have that on the bottom side, but we need some more texts. And should have that in 3 millimeters. See how that looks. Bottom silk screen. And if we say that and flip, yeah, we don't want that to be on the connector. I should make that a bit smaller. Because all the holes, drill holes here will destroy the text. So we just do it like that. And I would like to place a ground where there's a bit of ground here. Let's see if we can find the ground VM. And we'll also place one close here. Turn on the other layers and see if we make a problem here. There's nothing there, so we can just make a fill. So now we see that area has also been filled. Maybe we should just write a bit about the ESP32 there. So let's jump to the top layer. ESP32-C6 demo board. I think that's cool. All we need to do now is to verify that we don't have any clearance mistakes or any errors in the design. So we go up here to inspect and then run a design rule check. And we need to do that before we ship the PCB off, because if there are some mistakes, it's quite easy to correct them now instead of when we get the PCB and it's completely filled with errors or something is shorted. So let's do a design rule check and see if we have some potential problems here. So we see we have 29 errors and some warnings. So some of them are quite easy to get rid of. We see we have one unconnected item here. there is a net that has no connection, so we need to have a look on that. So we see this is this part, and we need a wire here. And now that should have been fixed. You see, this was very hard to see if we didn't make a design rule check that this pin was not connected to anything. So let's do another one and see if we have 28 errors now instead. So now we have 28, and the track has unconnected nets, so we need to find that one. So there's something wrong here. That's just a small dent there. Tools, inspect, design rule checker. And you see there are some violations because we are too close to some of the pins, but yeah, there's nothing to do about it. So we cannot really do anything. There's too less clearance here, but we need to have that track here so we can see, say, okay, this is just where it is. And this is all concerning the USB connector, or the USB signals, because we cannot really remove the pin from here. So this is a lot of things concerning the connector and the USB signals, but yeah, nothing we can do about it. And the silk screen has been clipped here. That's also no problem. Board edge violation. Yeah, this is too close to the board edge, but we will just verify that in a second. Clip by board. Okay, close. And then we go to File. Let's see, board setup, and we will say constraints, copper to edge clearance, so we will just do that 0.2 millimeters. And tools, inspect, design will check. And now that's also gone. So we still have some errors, but they are just concerning the signals we have for the USB. There's nothing we can do about that. So we know that our design, there are no more potential problems. So we are actually ready now to generate the Gerber data. Let's just have one more look on the design in the 3D viewer. I think that's fine. Let's have a look here on the back side. That's also fine. A very nifty small PCB, 50 by 50 millimeters with an ESP32 USB connection and temperature and humidity sensor here. User buttons, RGB LEDs, quick interface, what's not to like. So we say save, and you see I have a plugin here where I can just press a button here and then it will compile all the necessary Gerber data, and it will upload them automatically here to PCBWay, and you can start ordering the PCB shortly. And a lot of the things has been field. It detected 4 layers and the size, and then you can select if you wanted it another color, or the silk screen should have another color, or if you want another surface treatment on your board. So there's another way you can save the Gerber or generate them. You can say File, and then Fabrication Outputs, and I would like that to be Gerbers, and I want a output directory to be Gerber. I don't want to have all the Gerber files messed with my design files, so here I place them in this library. All the necessary files has been checked here, and now I just press plot here. The data has been generated, and I would like to have generated my drill files as well, and generate. And then if I go down here in my design library, I have the library here with all my Gerber data in a separate directory. That's it. Now we are just waiting for our design to be completed at PCBWay, and then we can solder up our prototype and get starting playing around with the ESP32-C6. So I hope you enjoyed the video, and see you in the next one. Bye.